So let's do some concrete examples. First, for Overwhelm, if you let R over L to be 1 and 1 over CL to be 1 over 8, we get y double prime, 1 y prime, and then 1 over 8. So this is the ODE, and its quadratic equation is r squared plus r plus 1 over 8. The solutions are minus 1 plus minus 1 over square root 2 over 2. So indeed, the b squared minus 4c, which is 1 minus 4 over 8, is positive. So indeed, it's overdamped. And so then the solution will be the following. C1, the general solution. Let me put everything in parentheses. So t times minus 1 minus 1 over square root 2 over 2 and minus 1 plus. Okay. And since a half is bigger than, or let me say this, since minus 1 is bigger than 1 over square root 2, we have a dominating behavior. So this guy will go to 0. So it will go as e to the minus t like that. Okay, as t goes to plus infinity, which again is reasonable, even though we have resistance. Okay, so let's watch simulation. So I'm doing the damped system. And we start from some initial data, and then indeed we decay down to the origin. As time goes by, it will hit the origin. Okay, good. Almost there. Done. All right. Now, next example. It's critically damped. So here you just let L to be 1, R to be 2, and C to be 1 gives y double prime qy prime plus y equal to 0. So that's the ODE. The system is r squared 2r plus 1 equal to 0. So you have the double root double repeated root. And as we did before, the general solution would be e to the rt, so e to the minus t, and then e to the minus t times the u of t, the u of x. So again, you can see this guy decays to 0. Let's do a quick simulation. Okay, so it comes back, tries to escape, and hits the origin in finite time, in fact, as far as we're concerned. But yeah, it never actually hits. So sorry, it's not finite time, it's asymptotic. Okay, next. So under damped with decay. I will explain. Here, let L equal to R equal to 1 and C equal to 2. This choice gives y double prime, y prime, and y over 2 equal to 0. The characteristic equation is r squared plus r plus a half. And the roots for this are minus a half plus minus I a half. Okay, so we have imagined. I mean, you can check. So we have b squared minus 4c, b is 1, 4 is a half. So you get minus 2, which is negative. So indeed, under damped. Okay. So the general solution is as follows: C1 e to the minus a half minus I a half t, and e minus a half plus I a half t. And you can write this in using Euler's formula as e to the minus t a half sine t over 2, sine, and cosine t over 2. And again, the exponential goes faster, so this goes to 0. These guys are between 1 and minus 1, so they don't affect the decay. So let's run the simulation. And again, here we have more rotation because it's periodic, but it still goes to zero. So observe that there's a spiral around zero. This is because of sine and cosine. So it curves into zero, but it still goes to zero. Okay, one more example. Underdamped with no decay. So what do? Zero resistance. So you can expect periodic behavior when there's no resistance because energy is conserved. And L is 1, C is 2. Gives y double prime plus y over 2 equal to 0. Sorry, times 2. No, over 2. So then we have r squared plus a half equal to 0. So r is equal to plus minus I 1 over square root 2. Okay. So this is the two solutions. So y general is equal to C1 e to the I square root 2 t and C2 minus I square root 2 t. And with Euler's formula, t over square root 2 and cosine of t over square root 2. This guy doesn't decay. As t goes to infinity. Instead, it's a periodic behavior. So let's go to MATLAB. So it goes around and around. And eventually comes back. And it keeps going actually. So it never stops. Okay. So this is reasonable since no energy leaves the system via the resistance. Okay, so these are our examples. Thank you.